Now let's get back to the interpreter implementation for lazy evaluation, LFAE. The concrete syntax of LFAE was just the same with FAE, meaning that function call syntax is just the same, just like before. So the concrete syntax for function call is gonna be E1 open E2. And when we evaluate E1, E2, remember that operation semantics under some environment, when we have E1, E2, how do we evaluate this thingy, right? And then we say under the given environment, evaluate E1 and its value is going to be closure B, which has the parameter name and body expression, and that environment. It's a different environment, right? And then evaluate E2, it's going to have value, say V. And what do? Evaluate the body expression. Ooh. What's going to be the environment? On top of that environment, when the closure was constructed, we extend that parameter's value is what? Parameter's value is argument value V. And evaluate the body expression E. Get the value of V prime. That's going to be the value of V prime. That's the semantics of FAE, right? Meaning that when we evaluate E1 and E2 right away, whenever we encounter sub-expressions, E1 and V2, in FAE, we evaluated them right away. Under the same environment, evaluate E1, get the value. Under the same environment, evaluate E2 and get the value. And then under this revised environment, evaluate the body expression, get the value of V prime, that's going to be the result. In LFAE, it's different, right? In LFAE, we interpret E1, the first sub-expression under that given environment sigma. And because the value is not always just closure V right away, it could be X per V, we need to strict it. And then get the value. And we do not evaluate E2 right away. We do not have a arrow thing. We do not have interp call here. Instead, we construct X per V. We construct a value with the argument expression E2 and environment sigma. And what? The catched result is going to be nothing. The type of the third field V was option of value. Remember? Yeah? It was option of value. So it's going to be what? Nothing. And then do the evaluation. So it's going to be none. We are not going to discuss the operation semantics of LFAE in this course. But you'd better be able to write that by yourself. That's how you can learn the semantics. Whenever we have the semantics, whenever we have a new language construct, we what? Explain the semantics in prose. We explain the semantics with the Scala implementation. Scala implementation of the interpreter. And what did we do? We wrote down the operational semantics. In LFAE, I explained its semantics in prose. In prose, meaning like defer the evaluation of the function argument until it is necessary. And then we implemented the semantics in Scala like this. And then I defer the operation semantics of that to you. You'd better do that by yourself. I'm gonna come back to this point in a minute after this very important slide that you saw in the beginning. Let's summarize what we have been discussing and get back to this important question. Again, LFAE, lazy FAE, share the concrete syntax with FAE, meaning that the concrete syntax of FAE and LFAE are the same. So when we write the same expressions here, if I don't say any language it is, you don't know its result, even though you have the concrete syntax. So if the first sub-expression is in FAE, the semantics is going to be evaluate E1, get the value closure V. Evaluate E2, which is addition of num V and closure V, which is an error. So in FAE, evaluating both expressions are going to be result in error. Error, both of them. Now, let's think about LFAE. Evaluating the first expression, we are going to call the strip function, right? We are going to call strip function for the first sub-expression, so we are going to get closure V, both of them. Evaluating the argument expression in LFAE, it's going to be what? X per V. We are not going to evaluate the addition of number and closure. It's not yet an error, not yet. In the function body, yeah, when we evaluate the first sub-expression, we interpret it and then strict it. For the second sub-expression, we just construct X per V. And then when the first sub-expression has a closure V, we evaluate the body expression. We evaluate the body expression. In the first example, body expression is 0. So we do not even look up the environment for X and just return num V0, which results in 0. So far, so good? Okay, how about the second sub-expression? Second expression, yeah. How about the second expression? Let's look at that. That's closure V, that's X per V, and then let's look at the body. Body expression is X. What's the semantics of X? Look up the environment. By looking up the environment, what do we get? X per V. That's the entire code. Does it result in error? Not really. The result of this function call in LFAE is what? X per V. With that argument expression, with empty environment and none. That's the result in LFAE. In the interpreter that we implemented, that's the semantics. Do you like it? What do you think? X per V is not really a value. Evaluating some expression could be real value like num V with some number or closure V with primary and body expression and the environment or error, right? These two are normal values and this is an exceptional erroneous result, but not X per V. It's nothing, right? So, if we want to make it an error, there could be several options, right? What are going to be such options? How can you make it an error? What do you think? What do you think? Number one, on the top level, after calling this interp of E, interp of expression and the environment, interp of E and the empty environment, we are going to get value, right? We are going to get value and then we can call strict in the top level. That's one option. Do you see that? Oh, yeah. That's one good option. What's the other? There could be many options like that, but what's What's going to be other option? You think about it. Take a moment and think. How can you throw an error when we have an expert V value for identifier? Do you see that? Yeah? We can call, what's the semantics of identifier in the inter function? Inter of ID, some environment. What's that? Do you remember? That's gonna be look up the environment with the name. Then what do we get? A value. So how can we throw an error for that? Strict. Right? Strict that expert V. Then you're gonna get the expected error. But the point is, whether to call strip function makes different semantics. Right? This LFA semantics, this top level strict function call semantics, this semantics of strictify for identifier lookup, they all result in different semantics. I didn't say that LFAE semantics is wrong. LFAE semantics will not throw an error for this expression, but result in expert V. That's one semantics, one lazy semantics. Number 0. So we are discussing 3 different semantics of lazy evaluation. Even with this one syntax, LFA, even with this one concrete syntax, we could have 3 different lazy semantics. LFAE implementation that we saw by now, calling strip function in the top level for this program, or calling strip function for every lookup of the identifier. They are all lazy, but differently lazy. Some is more lazy and the other is less lazy. Whether to call strip function, where to call strip function, how often call strip function makes the laziness. So I ask you to think about those different semantics. And as usual, we have these good documents both in Korean and English, and these documents even talk about operation semantics. Those operation semantics may be slightly different from what we discussed today, which is even better because you can think more about laziness and other similar lazy semantics. Okay, with that, we are going to be done with lazy evaluation. Again, this Wednesday, we are going to have some practice session about growing a language. And that's going to be a good exercise or exercises before the midterm exam. Thank you.